to the lecture series on deep learning techniques in medicine. I am Dr. S. Sivaranjini, Assistant Professor in the Department of Biomedical Engineering, SRM ISD, Katangarattur. In this lecture, we will be seeing about the Module 1, Introduction to Deep Learning, under which the activation functions, fully connected layer and the softmax layers will be covered. So moving on to the lecture, we will have the activation functions. So what are these activation functions? These are the ones that decide whether the output should be passed to the next layer or not. So what tells you that? And without these activation functions, what happens, right? So if we are, suppose we are removing all the activation functions, what happens? We already know that the linear equation will be z is equal to wx plus b, which will be expanded as w1 x1 w2 x2 plus w3 x3 goes on to wn xn plus the bias term b. Okay, so you go on, keep on stacking the linear layers. You will keep on stacking the linear layers and still the linearity of x is maintained. Okay, so the entire network, even though you have n number of hidden layers, you go on increasing the number of hidden layers, still the network will behave as a linear equation. Okay, so one linear equation will be the fitting target regardless of whatever be the depth. Therefore, it is not a deep learning. The depth becomes meaningless without the non-linearity, right? So why these activation functions are used? So they are the ones which decide whether the output should be passed on to the next layer or not. They convert the output of the neuron into a specific range of values. Okay, so the neural networks can provide very large or very small numbers as output, right? So they convert these output to a specific range. So what are they used for classification? The output must be 0 and 1. Okay, so these are the ones which gives you the essential of expressive power. These are essential for expressive power. Directly resolve the opening problem. Opening problem, which I told you, it becomes as a single linear equation, although you increase the number of or the number of depth or the number of hidden layers. Okay, so these activation functions scales the output to this required range, enabling them to capture the non-linear relationship of the data, not only the linear relationship, non-linear relationship of the data. As we saw in the previous videos, we saw that if a problem is not having a linear data, it is very difficult to do a classification over it, right? So if we are having a non-linear data, it is necessary that we need to use a activation function, right? They increase the expressive power of the neural network. So we have seen like what are these activation functions. Now what are the types of activation functions? So activation functions are represented by f of x, right? This f will be the one which gives you the activation function. What are the types are the sigmoidal activation function. What's the sigmoidal activation function? In the previous lecture on logistic regression, we have seen about this sigmoidal activation function. We will have a more deeper information over this section in this video. So f of x is equal to 1 by 1 plus e power minus 6. This is how a sigmoidal activation function is represented as. So what the output probabilities are? They are ranging from 0 to 1. Right? They are ranging from 0 to 1 and can be interpreted as probabilities only. It is not as real valued numbers. It's only the probability that a particular label or a particular class will belong to a particular input will belong to a particular class or a label. So a neuron which is using an activation is called as a sigmoidal neuron, right? As we saw in the previous video, they have the property of smooth and differentiable, and they are a monotonic function. So they are used heavily in logistic regression, right? And from the graph, we can see that whenever the values are in the negative side, whenever they go mostly on the negative side, the probabilities become 0, and when they move in the positive side, the probabilities are nearly equal to 1. And notably, if you see between -2 to +2, even a small variation of x will cause you a greater variation in the probabilities. Even a small variation from -2 to +2 will give you a large differentiation in the output. Right? So where they are commonly used as the binary classification, and they are used in the output layers. So earlier neural networks were using this sigmoidal activation function in the output layer. So we have seen like how it is used and where it is used, and the advantages of using a sigmoidal activation function for nonlinearity. Coming into the disadvantages, what this sigmoidal activation function does. This sigmoidal activation function gives you the vanishing gradient problem at extremes. What is this vanishing gradient problem? Whenever there is a backpropagation algorithm, training algorithm happening into a neural network or a deep learning network, what happens is like there should be a change in weight at each and every step, right? This change in weight is very minimal that it becomes negligible and it goes on reducing. It becomes at some point becomes 0. So this change in weight or the gradient vanishes off, and this is called as the vanishing gradient problem. So here how it is interpreted, it saturates near 0 and 1. So the derivative is automatically equal to 0, right? So this slows the learning in the deep learning networks, okay? And it is also not zero-centered. It is not a zero-centered. In the value of 0, you will be having some values, okay, right? So it is not zero-centered. When 0 is there, you have a value probability of 0.5. So it always gives you a output that is positive. That causes a zigzag gradient update. That gives you the zigzag gradient updates, right? So moving on to the next activation function, which is the tanh, or we call it as the tangent hyperbolic. This tanh activation function is defined by the equation f of x is equal to e power x minus e power minus x divided by e power x plus e power minus x. Okay. So these are used in the hidden layers, not in the output layers. These are used in the hidden layers as to make the mean of the hidden layer come to 0 or very near to 0. Okay, very near to 0. So this helps in learning the subsequent learning in the subsequent layers. So this activation function is a zero-centered activation function which helps to improve optimization of the network. Okay, so also because of this, there is faster convergence compared to the sigmoidal activation function. We have reduced bias in the gradients updates. Reduced bias in the sense the vanishing gradient problem is somewhat addressed here than the sigmoidal activation function. But still the vanishing gradient problem still occurs. Okay, even though it is stable, it is faster, still vanishing gradient problem occurs at extremes, right? The same saturation issue happens as in a sigmoidal activation function. You can see that it is zero-centered and it goes on. It has negative values ranging from -infinity to +infinity, right? So -infinity to -1 to +1 as it goes on increasing, right? The output range. The one which I'm mentioning is the output range. The output range is from -1 to +1. So the next activation function will be a rectified linear unit, commonly called as ReLU. This ReLU activation function is the one which we'll be seeing in most of the deep learning architectures nowadays. So this ReLU and its advancements also. So this ReLU activation function is defined as f of z is equal to maximum of 0, z. What is the 0, z? Maximum of 0, z. Z is the input, right? So what this equation gives you is like an output of 0 for negative inputs and it grows linearly for positive inputs. Here, the outputs will become whenever the inputs are negative. The value of x is in the x-axis, right? Value of x or the inputs. Whenever these inputs are in the negative side, it gives you the output as 0. Whenever it goes on increasing in the positive side, the value maximizes, or it gives you a higher range. It grows linearly, right? This is the default function for many types of neural networks, as I told you before. Also, it is computationally efficient as it does a thresholding operation. What is this thresholding operation? It's like when you expand this, when you are trying to explain this equation, f of x is equal to x if x is greater than 0, and if it is 0 if x is less than or equal to 0. The graph itself will tell you a straightaway answer. And it introduces sparsity in the network, as only a fraction of the network of the neurons activate at one point of time. Whenever the inputs are very less, below 0 or in the negative state, you don't even get the neurons passing on to the next one. Okay. So it helps in back propagation as its derivative is either 0 or 1. A straightaway thresholded answer. Right? And what are the main advantages is like computationally cheap with no exponential. We don't have any exponentials over here, and we don't have this vanishing gradient problem. For positive inputs, for negative inputs, it's a totally different case. For positive inputs, we don't have this vanishing gradient problem, right? So even though it has many advantages, one major problem is the dying ReLU, or we have the dying neurons. Okay, so what are these dying neurons? Is like if a neuron's weighted input stays negative during the training, the weighted input, the input x, the weighted input, when you are trying to multiply the value of your input with the weights, that becomes a weighted sum. So each and every weighted input comes to the negative size during training phase. The output is always 0 and the gradient is 0. There is no change in the weights, right? So the neuron stops learning permanently and it dies off. The neuron will not be used. It dies off and no neurons will be there. So it suffers from dying neurons. Okay, this is called as dying ReLU, right? So this is the major limitation that the ReLU has. Even though the limitations are there, it has major advantages such as faster training and avoids the vanishing gradient problem that limits the sigmoidal and tanh in deep level architectures, right? So as a comparative analysis for the activation functions, what we can say, we have the sigmoidal activation functions for a binary classification problem since the output ranges from 0 to 1. And for a tanh, what did we see? We saw it is 0 center ranging from -1 to +1. And for a ReLU activation function, it is ranging from 0 to infinity. So it is like a thresholded one. So it is very fast and there is no saturation for x is greater than 0. It goes on increasing linearly, right? So these are the types of activation functions and why these activation functions and what all applications you can use these activation functions was covered. Next, we move on to the fully connected layer, right? So we have seen that we have different layers in a neural network. What these layers do? So the input layer gets the input, no computation happens. The hidden layer does all the computations. It multiplies the inputs with the weights and then computes what kind of activation function to be used inside the hidden layer, and then what has to be passed to the next one to compute it, and then it goes on to the fully connected layer. Okay, this fully connected layer is a neural network layer in which every neuron in the current layer is connected to every other neuron in the previous layer. So it is connected to every other neuron in the previous layer. Okay. So each feature in the final spatial layer is connected to each hidden state in the first fully connected layer, which means that the final spatial layer or the hidden layer is connected to each hidden state. Each and every hidden state, it will be interconnected, right? As we saw in the previous lecture. So, and then it is passed to each hidden state in the first fully connected layer. It is connected to the first fully connected layer. And then from the first fully connected layer, every neuron will be connected to every other neuron in the current layer. Okay, right? So this fully connected layer is also called as a dense layer and is the basic computational unit of many networks, right? So this will be a major portion in a deep learning network. Okay, this fully connected layer combines the information from all input features and allow the network to learn complex feature interactions. What is this complex feature interaction? Whenever you require some complex features to be extracted, this fully connected layer will play a major role. So vast majority of parameters lie in the fully connected layer since they learn the complex feature interactions. So what happens? You do a feature extraction, then flatten it, and then flatten it in the sense we convert it into a 1D vector. This flattening will be a multi-dimensional feature map. Whenever you get a multi-dimensional feature map, you are trying to convert it into a 1D vector. Okay, so then it is these FC layers are passed to the classification to produce the final class scores. So what can be the alternative if we are not having a fully connected layer? What can be an alternative to the fully connected layer? Either or you have to keep it, right? So it can be replaced by an average pooling over the entire spatial area of final activation maps. Okay, what is this? We see with an example. Here we have the final activation map size to be 7 cross 7 into 256. Okay. This operation produces one value per feature map. Okay. This is the final activation map and it produces one value per feature map. Hence, the number of output features equal to the number of filters. What is this? The number of output features in the sense, after this, whenever you are using this global average pooling, what happens is like the last number, the number of filters that will be used in, that will be the output from the final activation map. The 256 filters that are used to obtain the final activation map will be the number of features that is obtained. Okay, so each feature is computed. How it is computed? Each feature is computed by averaging 49 values, right? 49 values obtained by 7 cross 7 becomes 49. Okay, so this is the alternative to a feature, a fully connected layer. So next, moving on to the next layer, which is the softmax output layer. Okay, softmax output layer is the one which converts a real valued score, a vector of real valued score into a probability distribution over multiple classes. Okay, if you're having multiple classes, you give each and every class a probability value and say that the input, if it has a probability of so and so values like 0.9, what type of class it belongs to. Okay, you give a score and then the probability is calculated and then it is decided whether it is a class A or class B or class C, whatever it is. Okay, so the output values lies between 0 and 1 and the sum of all the output values, the entire probability, the sum of the probabilities should be always equal to 1. Okay, so why this sum of the probabilities is equal to 1 here? Okay, so we will be, if to answer that, we need to see about the softmax equation. And one more thing is like this softmax output layer will be used for multi-class classification. If it is a binary class, we can use sigmoidal activation function in the final classification layer. If it is a multi-class classification, we have n number of classes. Class 1, class 2, class 3, class A, B, C, or it goes on. Right? When you're having so, then you can use a softmax output layer. So how the softmax output layer is calculated? Zi is equal to e power zi divided by summative value of j is equal to 1 to k e power zj. Okay, so this will be the individual score, exponential value of the individual score, and the summative value of the scores belonging to each and every class will be in the bottom part, the denominator part, right? So this summative value, when the probabilities are calculated, that value should be equal to 1. We'll see with the we'll see how it is calculated too. Okay, right? So this is the one which converts into probabilities, converts scores into probabilities, and emphasizes the largest input values, right? So it preserves the relative difference between the inputs, right? It preserves the relative differences between the inputs. So it is differentiable and it is suitable for back propagation. Okay, what is this back propagation? This is a training algorithm that is used for almost all the neural networks, right? Whenever there is a forward pass, you do a training through a back propagation algorithm. Okay, so why do we need a softmax? So we need it because the output are unbounded real values. To change this unbounded real values into probability scores that range from 0 to 1, we need this softmax, right? So the softmax normalizes the outputs and enables probabilistic interpretation. Okay. So how can we see this softmax layer? With an example. Okay. So we are having the input scores. Say for this is class A, this is class B, this is class C. Okay. After the softmax, these classes will have the probability scores of 0.6, 0.24 and 0.1. How these are calculated are, like if you are having a input score of 2, 1 and 0.1. You try to replace this 2, 1 and 0.1 into this equation. So for a value for class A, you are trying to give a value 2 and additive value of 2, 0.1 and 1. Okay. So when you are trying to get a value for class A, you get the probability with the numerator having the value 2 and the summative value, the exponential value of 2 and the summative value e power 2 divided by e power 2 plus e power 1 plus e power 0.1. Okay, that will give you the class probability of the class 1. Next, for the class 2, you calculate in the same way. For class 3, we calculate. So these are the probability values. So the interpretation will be class 1 will have 66% probability. Class 2 will be having 24% probability. Class 3 will be having 10% probability. Okay, so these are the input scores for a particular input, right, for each and every class. And then based upon this score, we can say this particular input belongs to class 1. Okay, so this softmax layer, thus it is used in the final layer of the neural network, which is applied after the fully connected layers and produces class probabilities. So so the decision is made on the class with the highest probability value, right? So having a brief summary, we saw about the activation functions and what are the different types of activation functions and what kind of applications require what kind of activation functions and where these activation functions should be placed. And then we saw about the fully connected layers, how the fully connected layers are used and what should be the what can be the possible alternative for a fully connected layers. And then we saw about the softmax layer, where the softmax output layer can be used and how the real valued numbers are converted into probabilities for prediction of the classes, right? These probabilities are converted into classes. Thank you.